you. So before I start, let me just explain this picture in the background. Some of you might not know. This is the Super Kamiokande experiment. This is 40,000 tons of water, 1.5 kilometers underneath the surface. 4 numbers that I will use were measured by this experiment. And first of all, I think it makes a nice background to the pictures because it's very aesthetic. But also, I like the following thing. So the way they fill it up with water, 40,000 tons of water. And here you can see a boat with 3 students. And the way it goes is that they fill a bit water, and then the students go around in the boat and clean the photomultipliers that you see around. Okay, so they clean one such, and then the water fills up a bit more, and they clean the next one and a bit more. And I always am thinking whether they remembered to put an opening up there. So I've written 3 papers and 1 contribution to proceedings with Nati. You can see here the titles and the list of authors. All of them have to do with flavor physics. And my basic assumption preparing for this talk is that Nati and I are the only flavor physicists in this audience. And so I will update Nati on what happened in the 20-something years since we wrote these papers. And for the rest of the audience, I'll give kind of a review of what I think are the important developments. It would be really an overview of developments in flavor physics over the last 20 years or so since we worked on this. So I think flavor physics is interesting for 2 different reasons. One is a probe of physics at energies that are much higher than what is accessible in accelerators. And the main reason for that are flavor-changing neutral currents, which is a class of processes that are uniquely suppressed in the standard model. There is loop suppression, there is CKM suppression, and there is Jim suppression, because of the small mass splitting between the first 2 generations of fermions. And many extensions of the standard model do not share these 3 or some or all of these 3 suppression factors. And so they could compete, be comparable, or dominate over the standard model, even if the new physics takes place at an energy scale as high as 100,000 TeV. So the hope is to find deviations and to discover physics that is not necessarily accessible, say, to the LHC. The other is a series of puzzles that are intrinsic to flavor physics. And this is my definition of 3 puzzles. These 3 puzzles may be related. They may have 1 answer. They may have 3 answers. They may have no answer. We don't know yet. But here are my formulation of these 3 puzzles. So the standard model flavor puzzle. In the standard model, there are 17 or 18, depending how you count, dimensionless couplings. And the 3 gauge couplings and the Higgs quartic coupling, which are not flavor parameters, are all what I would call order 1 random parameters. While among the 13 flavor parameters, there is a lot of smallness and hierarchy. They span some 6 orders of magnitude, and most of them are small. So there seems to be structure there, and the question of why there is structure in the fermion flavor parameters is, for me, the standard model flavor puzzle. Then, in the first decade of this millennium, we learned of another puzzle related to that. That's the neutrino flavor puzzle. As far as I can see, there is neither smallness nor hierarchy in the neutrinos. Everything that is related to neutrinos that we measured so far are order 1 parameters. I'll show it later. By itself, it would not be a puzzle, but given what we know about the other fermions of the standard model, the question is neutrino flavor different? And if so, why? So that's the second puzzle. And finally, the new physics flavor puzzle. So we have good motivation to think that there is new physics at the TeV scale. And the question is, if it is there, how come it did not dramatically modify the standard model predictions for flavor changing currents when it could, say, enhance them by many orders of magnitude? And it requires usually of this new physics, if it exists at the TeV, either degeneracy or alignment or a combination of these. So which combination, what is happening there, and why does the new physics have these features? That's the new physics flavor puzzles. And these are the questions, actually, these intrinsic puzzles, except the neutrino flavor puzzles that we did not know yet about when we worked together, were our starting point. We tried to understand plausible mechanisms that would give a solution to these puzzles. So the plan of this talk has 4 parts. In the first part, I will briefly review and extend a bit the work that I've done with Nati then, which is answering the quark flavor puzzle and extending it to the supersymmetric extension of the standard model. And then the important developments in this regard that took place over these 20 years, flavor in neutrinos, and Higgs as a tool to study further flavor physics. Let me just, and most of the audience are not phenomenologists, you may not recognize what these pictures are, except this one, which I already explained. So that's Super Kamiokande that gave us a lot of neutrino physics parameters. This is the Babar experiment in Stanford, one of 2 experiments that operated starting around 2000 and led to huge progress in understanding flavor in the quark sector. This is CMS, one of the experiments that did not find supersymmetry. So that's the quarks. And this is Atlas. This is Weizmann definition. Atlas is one of the experiments that discovered the Higgs boson. And so each of these is related. OK, so when I started working, let me say it this way. The work that I did with Nati had a huge impact on the topics that I chose to work on in later years, on the kind of questions that I was asking. And it started when Nati was still a professor in Rutgers University. And I was visiting there frequently and often for long visits. And one of the most memorable visits, we were given, my family and I, this fantastic 7-bedroom house, I don't know if you know it, in the botanical gardens of Rutgers University. And while my family were enjoying what is unique opportunity for Israeli families, snow-covered house and playing with snow, Nati and I were discussing the standard model and the supersymmetric flavor puzzles, which I will describe in the first 2 parts of this. Later, about 10 years later, I also spent a sabbatical at the Institute, and again had a lot of interaction with Nati. These are my 3 kids. This is a mythological picture in my family, because in one snapshot, you get the character and the relation between these 3, which completely describes them at those years and many years that followed. So it's really a picture that we love. They've changed since, so don't worry. Yeah, so Babar and Bell, and now also LHCb, made huge progress in our understanding of flavor physics, of the CKM metrics, of the Kobayashi-Scabrol metrics. And flavor physicists, for them, I think this picture summarized this progress. So rho and eta are 2 of the 4 CKM parameters that describe flavor changing physics. Most flavor changing concurrent processes, which are the ones that are sensitive, most sensitive to new physics, depend on these 2 parameters. And the various colored regions here describe the constraints from the measurements. And there are a few things to see from this plot, which is done after the B factories have finished their measurements. First is the richness of experimental results. We see here charmless B decays, mass splitting in the B sub D system and the B sub S system, CP violation in K to pi pi, CP violation in B to psi K short, CP violation in blue, in B to rho rho and pi pi, CP violation in B to D K. Many measurements, really, there are about 30 CP asymmetries that have been measured to better than 5 sigma. And that is after 36 years or so, from 1964, that we had essentially one measurement that we could interpret, epsilon, and another one that was hard to interpret. And here, a wealth of results that can be interpreted. Second is that this proved beyond doubt that the CKM mechanism is responsible to the flavor-changing physics that we are observing, and in particular, the Kobayashi-Mascara mechanism is responsible for the CP violation in meson decays. And this is demonstrated by the fact that all of these regions overlap. So there is a consistent answer within the CKM picture to all the physics of flavor violation and CP violation. Third is the fact that this is a very small region. This is not a manifestation of fine-tuning of any kind, but rather of the fantastic accuracy or precision of the experiment and the cleverness of theorists that suggested ways to overcome the hadronic uncertainties that are here everywhere and get very precise interpretation of the results. So that's why all these regions are narrow and why we can get a very precise answer. So I think we understand flavor and quarks. We know all the parameters there. And what Nati and I were interested in were not the precise numbers, so further progress here might be useful to discover perhaps new physics, but the standard model flavor puzzle, I think, is there, well-defined, and the accuracy will not lead to further progress in it. And what we found most attractive is to think that if there is smallness and hierarchy, it's probably related to selection rules that follow from an approximate symmetry. And there was the Frogat-Nielsen mechanism, which is, I think, the simplest example of an explanation of the standard model flavor puzzle. So let me describe it in one transparency. You assume that there is a horizontal abelian symmetry. Horizontal means that the different generations carry different charges. Simplest would be U1. There is a breaking parameter, explicit breaking, and it's small. And you assign it a charge, say -1. And then there are selection rules. Any term, say Yukawa term, that carries charge n is suppressed by epsilon to the n. And then you assign charges to the generations, and you check whether you can reproduce the observed smallness and hierarchy. And all of this can be embedded in a full high-energy theory, where instead of explicit breaking, you have spontaneous breaking by a scalar that is a singlet of the standard model gauge group, and the communication to the standard model particles of the breaking of the Frogat-Nielsen symmetry is communicated by vector-like fermions. So this is the general Frogat-Nielsen mechanism. And one of the questions is it testable? Could we explain any hierarchy and smallness, any set of parameters with this simple framework? And the answer that we found is no. There is one relation, order of magnitude relation. Relation means that the parameters are suppressed. The parametric suppression is the same independent of the charges, and there is a series of inequalities. So let me show you the predictive power of the Frogat-Nielsen mechanism in the quark sector. The one relation is that the smallest of the three independent mixing angles should have the same suppression as the product of the larger two. This is realized in nature too within a factor of 2. Remember, we don't have here control over the order 1 parameter, so that is fine. There is a series of inequalities. The mixing between, say, first and second generation must be less suppressed or comparably suppressed, but no more strongly suppressed than the ratio of the corresponding masses. So VUS, the Cabibbo mixing, must be larger than M up over M charm and M down over M strange, which is realized in nature. Mixing between second and third generation must be larger than the ratio between second and third generation quark masses, realized in nature. The third line follows from the previous three, but still it's okay with nature. So all of these inequalities are satisfied. And finally, something that before seeing that this is a prediction of the Frogat-Nielsen mechanism, I never thought about this as a feature. It's the following. Order the quarks by their masses. So rows are up charm top and columns are down strange bottom. And then the diagonal terms of the CKM mixing matrix are not parametrically suppressed. That's a prediction, and actually non-trivial, because for the neutrino sector, or for the lepton sector, for example, there are two possibilities for the hierarchy. There is something called normal hierarchy and something called inverted hierarchy. With inverted hierarchy, this is not actually the case. There are diagonal terms that are suppressed, and if that's the case, then the Frogat-Nielsen mechanism will be excluded by neutrino physics. So it's not a trivial effect. So all of this is realized in nature. These are all the tests that one can see for the Frogat-Nielsen mechanism within the quark sector. So it could be falsified. It is not. Are we convinced that this is the explanation? I don't think so. As I said, further accuracy in the measurement would not help here. So can we make progress in this or any other explanation? So this is just an example of an explanation of one of these puzzles. So to my mind, to make progress, we need new physics. Well, we need it for many things, but also for flavor physics. And the point to realize is that if the new physics, the new particle couples to quarks and leptons, then there are new flavor parameters that can be measured. This would be the spectrum of the new physics and the flavor decomposition of the new particle, or if you want, the strength of their couplings to quarks and lepton. And the new physics flavor structure, one can think about three broad classes. Minimal flavor violation. The idea it here exactly mimics the flavor structure of the standard model, or more mathematically, if you switch off the Yukawa matrices of the standard model, it gains a U3 to the 5th global symmetry. The three Yukawas are spurions that break the symmetry into U1 to the 4th electron number, mu number, tau number, baryon number. If in the presence of new physics, the three Yukawa matrices are still the only source or the only spurions that break the U3 to the 5th symmetry, then the model is called minimally flavor violating. So no new structure, flavor structure beyond the Yukawas. Second, could be that new physics has a structure, flavor structure, that is related but not identical to the standard model. That would be the case with the Frogat-Nielsen mechanism. Same selection rules for standard model and whatever extension you have. Or it could be unrelated or even anarchical. Now, if new physics is discovered, then probably the new physics flavor puzzle will be answered. We will see, is it degenerate, is it aligned, what is happening there? And at least in the technical sense, we will understand it. Standard model flavor puzzle, less clear, because probably the physics that is responsible to the structure of the Yukawa is taking place at a high energy scale, perhaps even the Planck scale. It's not directly accessible. And yet, I will argue that given such an opportunity, we can make progress even here. And the point that I'll make mainly in the last part of this talk is the following, that in the sense of flavor physics, the new physics is already there. The Higgs boson was discovered. It's a new particle for us. It couples, it seems, to quarks and leptons. And its Yukawa couplings are new flavor parameters that can be measured, and they can be used to make progress on these puzzles, and that I will explain in the last part. These are things that I've been working on in the last few years. Okay. So in 1997, I organized a workshop in Weizmann Institute with the title Dynamical Supersymmetry Breaking. This was the core of this workshop. I think quite a few of the people in the picture are here, 19 years older than then, but still. And I think, please do not contradict me, that it was a very enjoyable workshop, not only because of the 2-day jeep tour of the Judean desert and the lunch that we had overlooking the Dead Sea. But also, it was intellectually very stimulating. I think also, probably we would agree, perhaps except for Nati, that this was very much thanks to Nati. So Nati was extremely active in this workshop, and he knows how to do it. So he asked thought-provoking questions one after the other, and he shared with us generously his insights. And it made, I remember that I thanked him personally at the end of the workshop, because I was the organizer, but the success from the intellectual side was very much due to his contribution. So that was highly appreciated, and it was a joyful workshop. So squarks. You extend the standard model to the supersymmetric standard model, and you get some 80 or so new flavor parameters that can be measured. Okay? All the squark spectrum, all the flavor decomposition of squarks and lepton, A-terms, everything. So this is the present situation as far as experimental data are concerned in this regard. It's a very sad situation. We didn't find supersymmetry so far. Could have been beautiful, but it's not there, so we have to go back to quarks. And we know something about quarks from quarks. So this is again the same data that I showed before, the flavor changing nuclear current processes, now allowing in the interpretation arbitrary contribution to flavor changing nuclear currents, in particular in this case to BB bar mixing from new physics. And if there is new physics contribution to BB bar mixing, you can parameterize it by two parameters. Age is the ratio of the size of the new physics contribution to the standard model one, and 2 sigma is the relative phase of new physics to standard model. And what you can see is that the data are informative enough that we now know for sure that new physics contribution to BB bar mixing is smaller than 30% of the experimental value. So the CKM mechanism is dominant in BB bar mixing. And furthermore, if the phase is different from that of the standard model, which is here and here, then the constraints are even stronger, no more than 10 to 20%. So new physics is subdominant compared to the experimental values in BB bar mixing and in almost any other neutral meson mixing. And this is generic for new physics. You can translate it into supersymmetry. And so the mass square difference between the two relevant quarks, the ratio between that and their average mass squared, times the angle, the mixing angle between the squark mass eigenstates and the down and bottom flavor eigenstate of squarks, this product should be of the order of 0.07 or smaller, when in a generic supersymmetric model, you expect these parameters to be of order 1. So that is the supersymmetric flavor puzzle. Supersymmetry could modify, could enhance it by order magnitude or 2, and it doesn't. And it requires either degeneracy or alignment or a combination of the two. So this is a demonstration for this particular thing. So Nati and I investigated what's the implication of the Frogat-Nielsen mechanism for supersymmetry, making no other assumptions about the supersymmetric spectrum. And we find that the first prediction, which is surprising, is that within Frogat-Nielsen, if you make no other assumption, then the squarks are not degenerate and the leptons are not degenerate. However, the mixing angle, the relative rotation between the mass eigenstates and between the flavor partners of the quark mass eigenstates are small. For left-handed quarks, it's of the order of the CKM matrix. For the right-handed quarks, it's of the order of the ratio between the corresponding masses and the corresponding mixing matrix. And by the inequality that I showed before, this is a suppression factor. So Frogat-Nielsen predicts alignment. Okay, the rotation or the relative direction between flavor eigenstates and mass eigenstates in the quark and the lepton sector is small. This is what we call quark-squark alignment. It's an alternative to squark degeneracy. Then we found something more. The holomorphic zeros can play a role. So now we are in supersymmetry. We look at the breaking parameter of the Frogat-Nielsen symmetry epsilon. We take it to be a spurion, a background superfield. And so in the superpotential from holomorphy, you can employ powers of epsilon, but not powers of epsilon dagger. And that means that if a Yukawa term carries charge of the same sign as the charge of the spurion, then you cannot compensate it by powers of epsilon. So that entry in the Yukawa matrix is 0. So that was something new. The Frogat-Nielsen symmetry, when applied to supersymmetry, can induce holomorphic zeros in the Yukawa couplings. And if you have these holomorphic zeros, then you can get an alignment, smaller mixing angles than the naive thing without the holomorphic zeros. It can be more precise, the alignment, because you can have zeros in appropriate places. That solves a problem with the constraints from KK bar mixing, where the Kabibo alignment was not enough to satisfy it. So now it could be satisfied, but also entailed a prediction, because in the quark sector, the up and down sector are misaligned by the Kabibo rotation, then if this is satisfied, DD bar mixing should be close to the bound. So that was our work, the main points of our work on Frogat-Nielsen mechanism in the supersymmetric framework. And then we took different directions. So Nati immediately understood, this is part, by the way, of this roundtable discussion that Robert recommended before, that the new point was to view all ordinary supersymmetric coupling constants as spurions by viewing them as background superfields. And then holomorphy can play a huge role. It's not just some small technicality, but it's really an essential ingredient, and you can apply it to many important and deep questions. And the first paper that came almost in parallel to our work from Nati was this famous paper on the non-normalization theorem, where this holomorphy was playing a huge role by treating the coupling constants at background superfields. I also used later holomorphic zeros, in work with Michael here and Nelson and Yuri Sherman on gauge-mediated supersymmetry breaking, where we used the same idea to solve the mu problem with the help of holomorphic zeros. And since I am a phenomenologist, I was extremely interested in DD-bar mixing and followed all along the years. It was indeed measured close to the bound. However, CP violation there was not a discovery. It's small. And with the Fogart-Nielsen mechanism, there is no way to suppress phases. So the situation now is that it's not enough, and we need also some degeneracy of the order of a few percent between squarks if they are at the TeV scale, but that can come from a gluino contribution via RGE and not necessarily from the boundary condition. So yeah, this is a picture of the Zeiberg family and the Nir family hiking in the Galilee in Israel, going over some stream on a bridge, and that's the same stream and another bridge, the same two families now from above. And it made me think about, hiking with Nati in physics. So I think a few of the things that characterize working with Nati is that if there are two bridges, if there are two ways to cross the water, you take both, okay? You don't go one and forget about the other. You take both. You investigate, you analyze any toy example that you can do relevant to the question. You use every relevant technique that you know in order to handle this. You play with it from any angle that you can, because if you do it, I think that's part of Nati's philosophy, in the end you'll find a surprise. I think Nati is looking after surprises. I mean, he has a well-defined question well ahead, but his hopes for surprises on the way there, and more than by the final original goal. So when we started doing Fogart-Nielsen supersymmetry, we did not expect alignment. We stumbled on it. We did not expect holomorphic zeros. And then when holomorphic zeros came, then this is another thing I learned from Nati, is to notice the unexpected. I think that's many times when there is something unexpected, you ignore it, you go on. But Nati sees the unexpected as opportunities. So the unexpected makes him happy. And when he stumbled on these holomorphic zeros, he understood immediately the power of holomorphy to explain many things and went on from there. So hiking with Nati is fun. Okay, so neutrino data had a huge progress since our work. We now know 5 flavor parameters with amazing accuracy, 2 mass squared differences of the order of 10 to the minus 5 and 10 to the minus 3 EV squared, and the 3 mixing angle, first and second generation, second and third, first and third. So this is what we know now. We did not know almost any of this, I think, in 1994 when we worked. And neutrinos always surprise us. So also in this case, for flavor physics, not to mention other aspects of it, all of these were surprises. So let's start with the mixing angle. U mu 3, mixing of the second and third generation, it's almost the maximal mixing, okay, 0.7. So pi over 4 is the rotation angle. And obviously, this is an order 1 parameter and larger than any of the 3 CKM mixing angles that we encountered before. Mixing between the first and second generation in the neutrino sector, 0.6, another order 1 parameter, and again, much larger than any of the CKM elements. Even the third one that usually is perceived to be small is not so small. It's of the order of the product of the other 2, which is the natural thing to expect. It's comparable to the Cabibbo mixing, but this is mixing between first and third generation. It's a factor of 40 larger than in the quark sector. So that's the mixing angles. They are not small. About the mass ratios, so far we really know only 1 mass ratio in the neutrino sector, or actually a lower bound. Knowing the 2 delta m squared, then the square root of the ratio between them is a lower bound on one of the mass ratio, and it's larger than 1 over 6. This is larger than any of the mass ratios that we have encountered in the charged fermions. Okay? The biggest of these is mu over m tau, which is 1 over 17. This is larger, and again, it's not a small number. So I would argue that so far, there is neither smallness nor hierarchy in any parameter that is related to the neutrinos. And is this the case? And if so, why is it different from the quarks and the charged leptons? That's for me the neutrino flavor puzzle. Let me put here a word of caution and also tell you something which I find amusing about the community that does flavor physics. So this is the mixing matrix as provided to us by experimentalists and by unitarity. These are the 3 sigma ranges of these numbers. Now, the community stares at these numbers and they ask, what do we see here? Now, a large part of the community, I'm not included, by the way, sees this in these numbers. This is called 3B maximal mixing. There are hundreds, if not thousands, of papers trying to explain this. So B maximal mixing is because one of the neutrino mass eigenstates is a maximal mixing of ni mu and ni tau. 3 maximal is that another mass eigenstate is a maximal mixing of electron neutrino, mu neutrino, and tau neutrino. And the third state does what it has to do in order that the matrix is unitary. Okay, it has no. Okay, if that's the case, then this is really a revolution because this can only be explained by some non-abelian discrete flavor symmetry, something completely unexpected to my mind. It also requires, by the way, in most cases also fine-tuning, but let's forget it. The main prediction of this framework was this 0 here, so it was somewhat disappointing that this was measured and found to be 0.15, which is a bit far away. It did not stop the community from working on this, that's okay. Another part of the community, me included, sees this here, complete anarchy. I put 0.6 and not order 1 because it's a unitary matrix. You cannot have all the entries 1, and psychologically this is closer to here than just putting 1 there, so I put 0.6 everywhere. I don't see a structure here. I see complete anarchy. I mean, this is what we would expect naively in a mixing matrix that has no special structure. And the thing that I find amusing is that you could not think of 2 interpretations that are more different to the same numbers than these 2, right? Very, very special numbers, non-abelian discrete symmetries, or no structure at all, no symmetry. And it's the same numbers, okay, that we are all staring at. So what does it tell us about Frobenius? So maybe it's time to give one explicit example of a model. So that's the model. It's not just the simplest, as far as I know, but also consistent with SU5. So you take the 10 of SU5, which has the left-handed quark doublets, up singlets, charged lepton singlets, and you give the 3 generations charges 2, 1, and 0. You take the 5 bars, which include the down singlet and the lepton doublets. You give the 3 generations the same charge. Okay? It could be 0, could be 1. And then the predictions for the spectrum is a strong hierarchy in the up sector, the square root of that hierarchy in the down sector and the charged lepton sector, and anarchy in the neutrino sector. For the mixing angles, 2 small, 1 very small in the quark sector, and order 1 also. The prediction of this simple model is hierarchy in charged fermions, which is consistent with what is observed, and neutrino anarchy. As far as I know, this is the only interpretation of the data, almost the only interpretation of the data that is consistent with the Frobenius mechanism. If it turns out somehow that this is not the right interpretation, then neutrinos can exclude this idea. Okay, I come to the last part, the Higgs boson. So this is Nati's daughter, quite a few years ago, Effie, and my son, Uri. And they do what the children of physicists, I think, often do. They do some serious stuff on the computer, right? And what are the physicists doing at the same time? This is taking the same opportunity. We play. Yeah, I think it goes deeper than just this picture, which I still remember the occasion, and we really enjoyed. We put this thing together, we take them apart, we try to make things run surprisingly fast underneath tunnels. So that's what we do in physics, right? We play all the time, and I think that part of the joy of working with Nati is the feeling. He's a serious person, but still, with physics, he's playful. And that's a very nice experience to play with the physics. So we have now a new toy, the Higgs boson. What can we do with it for flavor physics and other aspects? So we know already quite a lot about the Higgs. Here's what we know about its decays, or most of what we know. So R sub F is the ratio between production cross-section times decay into a final state F, normalized to the standard model value. So if the standard model is perfect, then all of these numbers should be 1. And what we see is that the 5 measured things are consistent with 1. There is nothing here which is 10 or 0.1. I mean, it seems all to be around 1. There are 2 upper bounds, which are important for my purposes. Higgs to mu plus mu minus can no longer be larger than 7 times the standard model branching ratio. And Higgs to E plus E minus cannot be larger anymore experimentally than 400,000 times the standard model. And yet, this is a useful number, as I'll show in 2 transparencies. So even that crude measurement. Remember, Higgs to E plus E minus is extremely rare in the standard model because the U-cover of the electron is small. So the standard model is very definite in its predictions for the flavor structure of the U-covers. It tells us the U-cover is the mass matrix times square root of 2 over V, the vacuum expectation value. And I would argue that there are here 3 features that can be separated, and actually each of them can be tested separately by experiments, and each of them will teach us something different about solutions to the flavor puzzle. So one is proportionality. The diagonal entries in the U-covers are proportional to the mass, so y mu mu over y tau tau is m mu over m tau. The other is that it gives us the factor of proportionality, so the U-cover of the tau, say, over the mass of the tau is square root of 2 over V. And finally, there is here diagonality or alignment in the previous language of diagonal couplings at 3 level, at least R0. And these things are starting to be tested by experiment. So here is the picture of proportionality at present. It includes also the electroweak gauge bosons, so top Z, W, bottom, tau, the upper bound on the muon and the upper bound of the electron. This is the mass in GeV, this is the coupling, and the dashed line is the appropriate relation within the standard model, which for the U-covers is this slope of square root of 2 over V. We see that everything is consistent with being on the dashed line. So in particular, those of the third generation, top, bottom, and tau, which there is a range, are not far from the standard model. It seems that for the third generation, the ratio between the U-cover and the mass is indeed quite close to square root of 2 over V. And what is interesting is that the upper bound on the mu and the E U-cover is already smaller than the lower bound on the tau U-cover. So the trend is already there that the first 2 generations are more weakly coupled by the U-cover than the third generation, as predicted, but we are still far from measurement. But here we see that even this square root of 400,000 is already telling us that the U-cover of the electron is smaller than that of the tau. So this is the beginning of Higgs flavor physics. How about diagonality? It has been tested so far, or searched for, in 4 processes, T to Higgs and charm, and top to Higgs and up, Higgs to tau and mu, and Higgs to tau and E. Not observed. There are upper bounds as a result of that on the U-cover, the off-diagonal U-covers, 0.13 for the CH, and 4 per mil on the tau mu. However, there is a 2.5 sigma effect, and we are so much hoping for something new that we are looking at 2.5 sigma effect with interest. So this is the CMS measurement of Higgs to tau mu, central value of order 1%, and I said 2.5 sigma away from 0. So let's do an intellectual exercise, okay? I mean, the right way to think about it is here, upper bound. But we are allowed to do intellectual exercises. So what if the branching ratio of h to tau mu is not much smaller than h to tau tau? And this would be extremely surprising, extremely exciting, for 3 almost independent reasons. So let me tell you. First, it breaks an accidental symmetry of the standard model, U1 mu over U1 tau, so it's clearly beyond the standard model, and there is important information about the scale of new physics that break it. I'll show in a minute. Second, h to tau tau is not a flavor-changing process. H to tau mu is not only flavor-changing, but flavor-changing current process. So maybe it's a hint of flavor-changing currents at 3 level, which is a surprise. And finally, it requires that the Yukawa is not proportional to the mass matrix, and that I will argue is a strong hint that the Higgs sector is extended beyond a single doublet. So let me start with the violation of the accidental symmetry. So we know already that U1 mu, we've seen violation of U1 mu times U1 tau because we've seen the atmospheric neutrino oscillations which violate that. We have a good explanation of that from the famous dimension 5 terms, 2 lepton doublets, 2 Higgs. They explain neutrino masses and mixing. They explain why neutrinos are lighter than charged fermions. They break U1e, U1 mu, U1 tau. They break total lepton number. And because they break the symmetry, they actually allow for H to go to tau mu. But it's here loop suppressed, mixing suppressed, Jim suppressed. The Jim suppression here is very, very effective. This is about 10 to the minus 3 EV squared. This is about 10 to the 4 GeV squared. And so if you multiply these three factors, you get a prediction for the branching ratio, which is 10 to the minus 50, which even the most optimist friends that I have don't think it will be hard a bit. So we go to dimension 6, because we want to explain perhaps order percent branching ratio. Here we have the structure of Yukawa times phi dagger phi and a possible new flavor structure. So the Yukawa of the light Higgs has a piece that is proportional to the mass matrix, but another piece which is arbitrary, but is suppressed by V squared over lambda squared. If you want the branching ratio to be of order a percent, there is an upper bound on the scale of phi TV. So that's exciting because this is physics that will be accessible to the LHC, if correct. Flavor changing at tree level. Well, in all models where you have no bare mass terms for the fermions or for the leptons, and with natural flavor conservation, in particular a single Higgs doublet, H to tau mu is loop suppressed, and then you have V squared over lambda squared, alpha over 4 pi, and some off-diagonal coupling, which is similar to the Yukawa of the tide. Even just the factor of alpha weak over 4 pi is already smaller than 10 to the minus 2. So this is extremely challenging for model building. In particular, the MSSM with R parity conservation is excluded if the branching ratio is 0.01. And so there is the models with tree-level coupling are favored. And there are the two simplest possibilities are the addition of vector-like leptons and multi-Higgs doublet. Vector-like leptons doesn't work. If it gives a large enough H tau mu coupling, it also generates Z tau mu beyond the experimental constraints from Z to tau mu and from tau to mu mu mu. So this leaves two Higgs doublet model is the only plausible candidate. In a two Higgs doublet, indeed, there is a piece which has an arbitrary Yukawa in it. This is the Yukawa of the doublet that is orthogonal to the direction of the wave. It's arbitrary, and you can easily accommodate it. So that would be the favored possibility. Now I come to the flavor point of this thing. So what about the Froggatt-Nielsen? So the Froggatt-Nielsen has the power to relate the parametric suppression of different couplings from the upper bound of mu to gamma. This is, by the way, the strongest upper bound on any branching ratio. We know that the Yukawa of the mu must be smaller than about 10 to the minus 6. It's only smaller within the Froggatt-Nielsen mechanism. It's only smaller by a factor of 20 from the mu tau. So combination of experiment and Froggatt-Nielsen tells us that the mu tau cannot be larger than a few times 10 to the minus 5. What we need to explain such a large branching ratio is something which is 2 orders of magnitude higher. So this is an example how measuring new flavor parameters can shed light on possible solution to the flavor puzzles and test them, exclude them, or support them. The Froggatt-Nielsen mechanism will be excluded, as will be all other kinds that I know of solutions to any of the flavor puzzles, particular natural flavor conservation, minimal flavor violation, Froggatt-Nielsen. All of them will be excluded if this is correct. Okay. So I come to my conclusions. My time is up. So in the quarks, we've seen smallness and hierarchy. That motivates to think that it is an approximate symmetry that explains it. With quarks, we could have flavor paradise, but so far we don't. Neutrinos surprise us with anarchy, which leads to the conclusion that sometimes knowing more does not necessarily mean understanding better. In this case, I think it has only been confusing. In the Higgs, there are things that we can test diagonality and proportionality, and this is a huge opportunity for flavor, but please find a deviation from standard model so that we can say something useful about flavor. So, a few final things about working with Nati. My gratitude. I think I learned precious lessons. I tried to explain them how to ask scientific questions, how to search for the answers, and in particular, how to notice the unexpected. Along the years, I've interacted a lot with Nati. I learned about his way of mentoring the younger generation, about being generous in sharing scientific insights. So I feel privileged for having worked with him. Thank you.
Okay, we have time for a couple of questions. I just ask that people wait for the microphone to get to them.
I still have the feeling after these years when Nati takes the microphone of oy vey. What is he going to ask? Yes.
So being maximally optimistic, can you outline what can be discovered in the coming years and how it will affect this?
Unfortunately, the fall of the diphoton took me away from being maximally optimistic, I have to say. Yeah, what I hoped for, which is, well, what is plausible, is that, I mean, this for sure will be measured, the branching ratio of H to tau tau. I'm talking now in this context. This will be measured in the end. This is the only coupling to second generation that is guaranteed if it's the standard model value to be measured. It would be extremely interesting if there is an upper bound stronger than the standard model value. And this is being searched for in various ways and can be improved with statistics and systematics. And this is an example of a set of 3 measurements that could test each of the features that I said the standard model predicts: proportionality, the factor of proportionality. So H to tau tau is enough to test the factor of proportionality. The ratio between mu and tau tests proportionality even with a different factor, and tau mu measured diagonality. So my maximally optimistic is that we'll see deviations in some of these and not in the others, and then we can really make a huge progress in our understanding which of the solutions survives and which not. Of course, if supersymmetry is discovered, it's another opportunity, but I don't know to say anything about that.
One more short question. Michael?
So related to Nati's question, what's the time frame for settling this Higgs to tau mu?
Well, Higgs to tau mu, there is no time frame. For Higgs to mu mu, there is, because Higgs to tau mu, the standard model prediction is 0, or if you want 10 to the minus 50 at the moment. So, but we can go much better. I think we can go in order of magnitude. For Higgs to mu mu, we have to improve by a factor of 7 to get to the standard model value. I think that's within a few years will happen. So we will have information on second generation, which, you know, it could still be that the Higgs is responsible for the third generation mass, but not for the first 2 generations. It's kind of interesting. It has some motivation. So this will be, I think, the first test of it, and it will come within a few years.
Okay, let's thank Yossi again.